Bismillahirrahmanirrahim. Assalamu alaikum. This is lecture number 13 of unit number 2. The title of unit number 2 is Matrices and Determinants. This is the last topic of unit number 2, means this is the last topic of the first term course. The topic of this video lecture is system of linear equations. In system of linear equation, we will discuss homogeneous and non-homogeneous linear equations, and all the equations must be in 3 variables. So you see that in this system we have 3 equations. This is equation 1, let's say this is equation number 2, and let's say this is equation number 3. These 3 equations are linear equations in 3 variables. You see that in each equation xyz is given, is xyz is present, and these are the variables a1, b1, c1, k1 are the constants of the first equations, in which a1, b1, c1 are the coefficients and k1 is the constant, and similarly a2, b2, c2 and a3, b3, c3 are the coefficients of x, y, z in equation 2 and equation 3 respectively, and k2 and k3 are the constants. So if k1, k2 and k3 are non-constants with the coefficients of the variables in all equations are non-zero, so this system is called the system of non-homogeneous linear equation in 3 variable. So in this video lecture we will discuss the solution of such type of system of non-homogeneous linear equations. And if k1, k2 and k3 equal to 0, so then this system will become homogeneous. Homogeneous mean the degree of the variable in each term is same. So you see that here the degree of the variable is 1, here is 1, here is 1. So you see that here is in all 3 terms the degree of the variable is 1, 1, 1. Here the degree of the variable in all 3 terms are 1. So this is a system of homogeneous linear equation in 3 variable. So in this video lecture we will also discuss the solution of the system of homogeneous and the system of non-homogeneous linear equation in 3 variables containing 3 equations. Okay, so this is the target of this video lecture. Before to discuss the solutions of homogeneous and non-homogeneous system of linear equations in 3 variables, first of all we will briefly revise the geometrical meaning of the linear equations and the solutions, about the solutions, that when the unique solution will exist, when infinitely many solutions will exist, and when no solution will be of the system. So you know that linear equation in 2 variable, if I start from basic linear equation in 2 variables, the standard form or the general form is ax plus by equal to c, or you can write plus c, let's say equal to k, and k is not equal to 0, where a is not equal to 0 and b is not equal to 0. So this equation is non-homogeneous because in this term the power of the variable is 1, here the power of the variable is 1, but on the right side there is a constant, here the power of the variable is 0. So that's why this is a non-homogeneous linear equation. This is a non-homogeneous linear equation in 2 variable. Geometrically this gives a straight line. The graph of this equation is a straight line in a plane, a straight line in a plane. So this is the graph of this linear equation in 2 variable. We already discussed this. This is x-axis and this is y-axis. Okay, now if k equal to 0, so then this equation will become homogeneous linear equation in 2 variable. And remember, the graph of the homogeneous linear equation in 2 variable will always pass from the origin. So let's say it may be in this direction or it may be in this direction, but remember that it will be always pass from the origin. This will be when k equal to 0, mean homogeneous linear equation. Now if I write two linear equations non-homogeneous combinedly, so that become the system of, let's say this is k1, this is a1, b1, a2, and this is b2, k2. So if k1 and k2 are not equal to 0, and also the coefficients of the variables in both equations are not equal to 0, so this is called the system of non-homogeneous linear equations in two variables. When you combinedly write two or more than two equations, so that become a system. Now you know the graph of, let's say this is equation 1 and let's say this is equation 2. So you know that the graph of the linear equation in two variables is a straight line in a plane. So you see when you discuss the solution of this system, so the solution of this system means the point xy of the plane which satisfies both the equations. So that's why they are also called simultaneous system of simultaneous non-homogeneous linear equation in two variables. So if I draw the, let's say when there are three possibilities, maybe a unique solution, mean you get a unique value of x and y which satisfies this equation as well as this equation. So this is one possibility. Then another possibility for the solution is it may be infinitely many solutions, mean there are infinite values of x and infinite values of y which satisfies both the equations. And the third possibility for the solution is that there is no value of x and y which satisfies the equation number 1 and equation number 2, mean the system, so that is no solution. So when I draw the graph of, let's say this is the graph of equation number 1 and let's say this is the graph of equation number 2. So in this case you see that both these graphs intersect each other at this point. So let's say this is x1, y1. So you see that the point which lies on the graph of the equation is actually the solution of that equation and that will satisfy that equation. So if you draw the graphs of these equations and they intersect each other at a single point, so in that case the system has unique solution, because this point lies on the graph of equation 2 as well as on the graph of equation 1. So in this case the system has unique solution. Now if you draw the graphs of both linear equation in two variables which are straight line in a plane and both the straight lines are parallel, let's say this is the equation of the graph of the equation 1 and let's say this is the graph of the equation 2. So you see that both the graphs are parallel. So in this case no solution. You see that there is no intersection, so in this case you will get no solution, mean you will get no value of x and y which satisfies both the equation. Here you have a unique solution. And similarly if I draw, let's say the graph of the equation number 1 is exactly lies above the graph of the equation number 2, mean both the straight lines lies on each other. For example like this, you see that both the marker lies on each other. So in that case there are infinitely many intersection points, mean all points are intersected with each other on both lines. So in this case we have infinite solution. Each point lies on this line which are actually two lines which lies on each other will satisfy the given equation. So in this case we have infinite solutions. So these are the three possibilities for the system of linear equation in two variables. Remember, the linear equation in two variables geometrically represent a straight line in a plane. Now we are going towards the systems which contain linear equation in three variables. So first of all, we will explain the geometrical meaning of the of the linear equation in three variables, that what geometrically linear equation in three variable represent. So remember, linear equation in three variable represent a plane in three-dimensional space. If I consider a linear equation in three variable, ax plus by plus cz equal to k, and k is not equal to 0, along with the coefficient of the variables are also not 0. So this is the linear equation in three variables. This is the linear equation in three variables, and this is also non-homogeneous because k is not equal to 0. So this is non-homogeneous. Geometrically, the linear equation in three variable represent a plane in three-dimensional space, a plane in 3D, three-dimensional space in which we are living. So this is, let's say, x-axis, this is y-axis, and let's say this is z-axis. So the graph of the linear equation in three variable is actually a plane in three-dimensional space. This is a plane in three-dimensional space. So this is the geometrical meaning of the linear equation in three variables. Okay, if I now consider three linear equations togetherly, for example, let's say a1x plus b1y plus c1z equal to k, and a2x plus b2y plus c2z equal to, let's say this is k1, this is k2, a3x plus b3y plus c3z is equal to k3, and let's say k1 not equal to 0, k2 is not equal to 0, and k3 is not equal to 0, along with the coefficients of the variables in all equations are also non-zero. So this is a system because you combine three equations, you write collectively three equations. So this system is the system of non-homogeneous linear equations in three variables. So we can find its solution. Now actually there must be three planes. If three planes intersect at a single point, so that single point must be order triple in 3D. If these three planes, actually this is a plane, this is a plane, and this is a plane. So if these three planes in three-dimensional space intersect at a single point, and let's say that single point is T1, T2 and T3, that must be, if these are the planes in three-dimensional space, so if they intersect at a single point, all these planes, so that point of intersection must be the point in three-dimensional space having coordinate T1, T2 and T3, mean distance on x-axis, on y-axis and on z-axis. So in that case you will get a unique solution if there is a unique point of intersection of three planes in three-dimensional plane at a single point. So in that case you will get a unique solution. If three planes lies on each other, mean every point of each plane is intersected with the points of the other two planes. So in that case we get infinitely many solutions. And if there is no intersection, or just two planes are intersected and one plane is not intersected with the other two, so in that case we get a no solution. So these are the three possibilities which I also discussed for the system of linear equation in two variables. Now we are interested in the solution of how we can find out the solutions, what will be the procedure. So for the system of non-homogeneous linear equation in three variables, we have three methods. To find out the solutions. The three methods are, the first method is matrix inversion method, Gauss elimination method, in which we converted the augmented matrix into the echelon form, and the third method is the Gauss-Jordan method, in which we convert the augmented matrix into reduced echelon form, and the fourth method for the solution of the non-homogeneous linear equations in three variable is Kramer rule. So these are the four methods which we will use for the solution. But before to discuss the solutions of the non-homogeneous linear equations, first of all we will discuss about the solutions of the homogeneous linear equations. A1x, I am taking the homogeneous linear equations from this system, mean I am taking k1, k2 and k3 equal to 0. So that will become the homogeneous. First of all we will discuss about the solutions of the homogeneous linear equations, system of homogeneous linear equations, and after that we will discuss the non-homogeneous. So this is a1x plus b1y plus c1z equal to 0, a2x plus b2y plus c2z equal to 0, and a3x plus b3y plus c3z equal to 0. So this is the system of homogeneous linear equations in three variables. I am discussing the solution, that how we can find out the solutions of this system. So if I substitute x equal to 0, y equal to 0 and z equal to 0. So for x equal to 0, y equal to 0 and z is equal to 0, all these equations are satisfied. So order triple 0 0 0 is the solution of this system, because for the value of x equal to 0, y equal to 0 and z is equal to 0, all the three equations are satisfied. So it means that x equal to 0, y equal to 0 and z is equal to 0 satisfies the system. So if it satisfies the system, so it means that this is the solution of the system. So this solution is called zero solution or trivial solution. Zero solution or trivial solution. Now if we have a value of x, a value of y and a value of z not equal to 0 and satisfies all these three equations, so that solution is called, for example, that solution 1 2 3, so you see that all the values of x, y and z are non-zero. At least if one of them is not 0, so that will be also known as non-zero solution, and non-zero solution is called the non-trivial solution. Non-zero solution, which is also called the non-trivial solution of the system. So when trivial solution and when non-trivial solution will exist for the system of homogeneous linear equations in three variables. If I write the left sides of the system in a matrix form, mean if I write the left hand side of each equation in the system in a matrix, for example like this, a1x plus b1y plus c1z, a2x plus b2y plus c2z, a3x plus b3y plus c3z. So this can be written as a1 b1 c1, a2 b2 c2, a3 b3 c3, and this will be x, y and z. So this matrix, if you multiply these two matrices, you will get this, and this is actually the left hand sides of this system, mean the expressions which contain 3 variables and all the variable has power equal to 1. So you see that this is 3 by 3 and this is 1 by 3. Sorry, this is 3 by 1. So in this row, in this matrix, the number of the columns are 3, and in this matrix, the number of the rows are 3. So compatible for the multiplication, and when you multiply, you will get this. Okay, so this matrix, you see that in first row this contain the coefficient of x, y, and z of the equation 1. These are the coefficient of the x, y, and z in equation 2, and these are the coefficient of equation number 3 of x, y, and z. So this matrix is called coefficient matrix. Coefficient matrix, and this is a column vector of variables, because x, y, and z are the variables. So this is a column vector of variables. Okay, if the determinant of this, let's say this matrix is denoted by capital A, the coefficient matrix is denoted by capital A, and the column vector of the variable is denoted by capital X. So if the determinant of this matrix is not equal to 0, mean A is non-singular. A is non-singular. So in that case, A is invertible. So if I write this into, now this will be equal to 0, 0, 0. So this is a column because they are all equal to 0, 0, 0. So this is actually a column vector of constants, and each constant is 0. So let's say for this, I am representing this matrix by A, this by X, and this by capital 0, capital O, because this is a null matrix. So this system can be written as Ax equal to 0. So this is the actually you see that I am converting this system into the matrix form. This is the matrix form of this system. Now if, remember this point, you see that the system of homogeneous linear equation in 3 variable is converted into this matrix form, where A is equal to A1 B1 C1, A2 B2 C2, A3 B3 C3, which is called the coefficient matrix of the given system. Coefficient matrix of the given system. You see that this is your system. When you convert it into the matrix form, so that is the matrix form, where X is the column vector of variables. This is a column vector of variables, and this O will be equal to 0, 0, 0, column vector of constant, which is a null matrix. So if, remember this point, this is an important point, if A determinant is not equal to 0, so it means that A is invertible, mean the inverse will exist. So if the inverse exists, and that inverse is denoted by A to the raise minus 1, so I can apply that inverse on both sides from the left hand side. So multiplying that A inverse from the left hand side, so you see that will become when matrix and its inverse are multiplied, so you will get identity matrix. So from here you will get identity matrix of the same order. A is the matrix A is, and from here you will get identity matrix. You will get null matrix, because a matrix multiplied by null, you will always get a null matrix. So you see that X equal to 0. So this implies that X, Y, and Z is equal to 0, 0, and 0. So this implies that X equal to 0, Y equal to 0, and Z is equal to 0. So from this we conclude that when a matrix is invertible, mean A inverse is exist, mean A determinant is not equal to 0, mean A is a non-singular matrix. So for that case, the system of homogeneous linear equation in 3 variable has a trivial solution, and that is the order triple: X equal to 0, Y equal to 0, and Z is equal to 0. And next important point, if A determinant equal to 0, mean a matrix A which is a coefficient matrix, and that matrix A determinant equal to 0, mean the matrix A is a singular matrix. So in that case we will get a non-trivial solutions. mean non-zero solutions. So we will get non-trivial solutions. So these are the two important points for eta. This is a system of homogeneous linear equation in three variables. It has a trivial solution, mean zero solution, if the determinant of the coefficient matrix is not equal to 0, mean non-singular. And if the determinant of the coefficient matrix equal to 0, mean A is a singular matrix. So in that case you will get non-trivial solutions. Now I am taking an example to explain this point. Okay, so you see that, okay, so these are the two important points. Okay, if a system has a unique solution, or if a system has infinitely many solutions, that system is called consistent system. And inconsistent systems are those systems which has no solution. So remember these 2 points in your mind. Now moving towards the augmented matrix, that what is the augmented matrix? If I, okay, this is about the solutions of the system of homogeneous linear equation in three variable. These two are the important points. If a determinant equal to 0, so you will get a non-trivial solution, non-zero solutions. If a determinant is not equal to 0, mean a is non-singular, so in that case you will get only a trivial solution. These 2 points are important for the solutions of the homogeneous linear equations in three variables. And inshallah we will take the examples from the exercise 2.4. okay, in next video lecture inshallah we will discuss about the system of non-homogeneous linear equation in three variables, and that will be the continuation of this video lecture.